Let's do a quick review of the derivative from single variable calculus. The goal is to find the slope of the tangent line to a curve at a specific point. The problem is that we need 2 points to apply the slope formula, and this only gives us 1. So we get at it by taking a second point on the curve and using that as an approximation to the tangent, then bring those points closer and closer together. We called that process a limit, and that's what gave us the formula for the derivative of a function. When transitioning to vector-valued function, the formula doesn't change very much. Definition. The derivative of a vector function r is defined to be this formula for the values of t at which the limit exists. We also use the notation dr dt and ddt of r of t for r prime of t. We will look at the computational consequences of this formula later. For now, we'll focus on the geometry of the formula. The vector r of t plus h minus r of t is the vector that points from r of t to r of t plus h. So the derivative captures the direction of movement between these points. Remember that this is being divided by h for small values of h, so this will stretch out the vector beyond those 2 points. And we're taking the limit as h goes to 0, just as before, which is bringing us closer to the tangent vector. And that is exactly what the derivative of a vector-valued function represents. The derivative is the tangent vector to the path. Since physics is one of the main applications of vector calculus, we're going to do a quick review. In physics, we can talk about the position of an object by using a vector. The idea of velocity is how quickly your position is changing with respect to time, so the derivative of position is velocity. Acceleration is the change of velocity. Intuitively, if you're speeding up, then your velocity is increasing, and if you're slowing down, then your velocity is decreasing. Speeding up and slowing down are accelerations, and acceleration is the derivative of velocity. It's very important to remember that position, velocity, and acceleration are all vectors in this context. They have both a magnitude and a direction. This is different from speed, which is the magnitude of the velocity vector, and it is a scalar quantity. You need to be careful with these, as it is common for people to use velocity and speed interchangeably depending on the specific context. So just be aware that you will have to pay attention to the situation and not blindly rely on formulas to get yourself through. The formula that we saw earlier shows that the derivative of a vector-valued function is calculated component-wise. The logic for this is much easier to see if we write the vector r using standard unit vectors. If r of t is equal to x of ti plus y of tj plus z of tk, then the derivative is x prime of ti plus y prime of tj plus z prime of tk for those values of t at which x, y, and z are differentiable. This should be intuitively true if you just notice that the vectors I, j, and k are constants. With that observation, the x, y, and z functions are just being multiplied by a constant, and those constants can be pulled out when taking the derivative. And if you look at the formal derivation in the book, that's exactly what happens. Because of this, the properties of the derivatives of vector functions will feel very familiar. The derivative of a sum of vectors is the sum of their derivatives. This is exactly the same thing as we saw in single variable calculus. The derivatives of products work out to behave like the product rule, even when taking derivatives of dot products and cross products. The reason for this is that if you look at the formulas for the dot product and the cross product, you will see that you end up with a sum of a bunch of terms that are just the product of 2 functions at a time. And that's where the standard product rule shows up to create the pattern in the final results that we see here. With the chain rule, the standard unit vectors can be pulled out, and you're left with the chain rule for single variable calculus. You really ought to take the time to prove these for yourself. Just start by writing r as the sum of its components with the corresponding unit vectors, and see where the manipulation takes you. This usually feels a bit clumsy at first, and that's just from a lack of experience. The best way to get experience is to do the calculation yourself and see how the pieces come together. One of the big applications of single variable calculus is finding the tangent line to curves. Let's review. If we graph the function y equals f of x, we get a curve. If we pick a specific value of x, say x equals a, then we can plug that in to get a point along the graph. The derivative at that point gives us the slope of the line. To get the full equation of the line, we start from the point-slope form and plug in the values, and after a couple algebra steps, we get the equation of the tangent line. The book calls this L of x, and is often called the linear approximation of f at a. We can do the same thing to curves in 3 dimensions. Remember that we need 2 pieces of information to get the equation of a line, a point and a direction. If we pick some specific value of the parameter, say t equals a, that will give us the location of a point on the curve. And then we can use the derivative of the vector function to give us the direction vector. Instead of using point-slope form, which only applies to lines in the plane, we use the vector form of the line. We're using the parameter s instead of t for now, to emphasize the idea that the parameterization of the tangent line can be done independent of the parameterization of the curve. We can plug in the point and the direction vector, and that gives us a parameterization of the tangent line. In this form, setting s equals 0 gives us the point on the curve, and there are many situations where this is useful. However, there are times when it's more useful to parameterize the curve so that s equals a gives us the point on the curve, which requires a slightly altered parameterization. In some ways, this is the more intuitive result because it means that the parameterization of the tangent line makes it so that the curve and the tangent are parameterized to meet up exactly at the point of tangency. Notice that this second form looks a lot more like the equation for the tangent line from single variable calculus, which is another reason why this form is often preferred. In the next video, we're going to take a look at integrating vector functions and look at some more physics.